All right. So last time we left off here with this general solution, or this solution to the fourth order differential equation here. And I talked about how that first term, right, represents a solution that increases with x, but we want a solution that dies out with x, because the farther x represents the position along the length of the beam, measured from the applied force or applied load. And so since the response of the beam will dissipate with distance from the load, we want this part of the solution. So we force the first two constants to 0, and then that just leaves us with two constants that we need to determine using boundary conditions. So here, this first part, right, eliminating those first two constants leaves us with a solution that simplifies down to the last term in the boxed equation above. And for simplicity, we will replace the exponent times sine or cosine with expressions in the form of a capital A, a capital B, and so on. I'll go through those on the next page, but basically what this does is it saves us some time in writing all of that out. So we have an expression for deflection that would look something like this. We'd have a constant C3 times capital B beta x plus a constant C4 times capital D subscript beta x. So these B and D subscript beta x represent the product of the exponent times sine and cosine respectively. So this here is our starting point for solving problems. And on the next page, we have the full definition of those terms. So we'll look at that. And there you go. So here we have the table 1 on the left, and we're going to use this to find numerical solutions to these problems, or to get values is what I meant to say there. So first I want to focus on the right side of the page though. Here, these first 4 lines have the definition of, here's that B beta x and D beta x, right? But there's also terms A and C beta x. And so we can see that A is simply equal to B plus D. Could say B is equal to A minus D then. C is equal to D minus B, and so on. So, or I guess I can go ahead and write the last one. D is equal to A minus B. All right, so these expressions are evaluated over in this table. All right, so this is, here we have these evaluated at beta x. And remember what beta is. It's that factor that represents the ratio of the foundation stiffness to the beam flexural rigidity, or the beam stiffness, right? So you have that factor that accounts for the relative stiffnesses of those two elements, and then x is a variable distance measured from the point of the applied load or moment. So the product of beta times x is what you plug in to evaluate these expressions. And one convenient way to do this is to just evaluate that product, look it up in the table, and then find the result that you're looking for in terms of one or more of these expressions, right? So beta x, you enter that table with that product, and since beta, we defined it as having units of 1 per inch or 1 per millimeter, the product of beta times x has no dimension. So you would input that as radians if you were to plug it into these expressions, and that would get you the results here. All right, so back to the right side of the table or the page, we have here a derivative table. All right, so I'm going to note that is, we're going to refer to this quite a bit actually. And the way this is arranged, right, essentially, if you know what order of derivative you're evaluating, say second derivative of moment is deflection, right? So you have your expression for moment in terms of A, B, C, or D, beta x. Then you want to take the second derivative of that to get deflection. You would say, okay, well, I have, let's say, second derivative of C. All right, so go to the second derivative column, find C, and then relate it to A. So C, the second derivative of C is related to A by a factor of 2 beta squared. All right, so you just have to move that over to the other side to get the actual second derivative. So we'll go through this in the example, but that's how to think about this table. Kind of have to work a little bit backwards to use it, but it's pretty convenient the way it's set up. And then the integral table down below can also come in handy. That one's a lot simpler, but we'll be using the derivative table more than we will be using the integral table. All right. So then the next handout sheet shows the effects of a beam on elastic foundation due to a point load on the left side and a moment on the right side of the page, right? So this is an infinite beam, and we have the deflection, right, shown in the first plot below the beam, the slope shown in the second plot, and then moment in the third, and shear in the fourth. So we'll come back to this as well at some point in the next couple days and look at a few things. So you can see here you've got the values noted for these items at the maximum location, right? And then in the example, we're going to look at this scenario, right? The example that we're going to do next. So we're going to consider the effect of an applied concentrated moment on an infinite beam on an elastic foundation. All right, so here it says couple at x equals 0. So that's just a reminder that we set our origin at the location of the applied load for these analyses. And as you can see, all right, the deflection from an applied moment is anti-symmetric about x equals 0. So that just means that y evaluated at negative x is equal to negative y evaluated at x. since the deflection is antisymmetric, the moment within the beam will also be antisymmetric about x equals 0. So with that information in mind, we can simplify this problem by essentially taking half of the infinite beam, all right? So thinking of it as a semi-infinite beam with one end at x equals 0, where the moment is applied. So if we do that, we would have to reduce the applied moment by half, all right? So we would apply 1/2 of m naught in the same direction. All right, and then the deflected shape would look something like that, right? With the magnitudes decreasing with distance from x, or the maximum magnitudes decreasing, right? So that deflection would be your lowercase v of x. So to analyze, right, any of the internal forces, deflection, slope, etc. for this beam, we would want to start with our starting point, all right, the deflection equation that we came up with on the previous couple pages ago, right? I'll rewrite it here. So that's that lowercase v of x is equal to e to the negative beta x times constant C3 sine beta x plus constant C4 cosine beta x. And we'll simplify that with C3 times capital B beta x plus C4 times capital D beta x. So this has the potential to get a little bit confusing just because we have constants that we start out with, but then we also have a capital C that we use for some of these expressions, right? So just make sure you keep it straight if it's a capital C with a subscript beta x versus a constant. So to get those constants, we need to apply our boundary conditions. So what boundary conditions would we be able to use in this scenario? Yes?
Deflection is 0 at the origin.
Yep, deflection is 0 at the origin. That's 1. Is there anything else that we know?
Deflection is 0 when beta x equals 2 pi.
Ah, okay, so good thinking, but beta x, that the wavelength isn't necessarily 2 pi. Yeah, so we'll get into that later, but yeah.
Deflection's also 0 at infinity, right?
Yes, yeah, but infinity is a really inconvenient number to plug in.
True.
I actually haven't tried that. Maybe it would work, maybe not. But so remember that the applied moment is considered to be a known value or a known quantity, right? That's not going to change. So we can treat m naught as a known, right? And then say we know the moment at x equals 0. So that would be our other boundary condition. So at x equals 0, we have deflection will be 0. So plugging that into our expression, all right, that means we have C3 times B of beta times 0 plus C4 times D evaluated at beta times 0. So if we go to the previous page, or I guess it's 2 pages back that has the table, all right, and we look at beta x is equal to 0, b beta x is equal to 0, and d beta x is equal to 1 in that case. So with that information, all right, we just come back and say that's 0, that's 1. And so this tells us that the constant C4 must be equal to 0, which means that our expression for deflection is only tied to that first term of our general equation. So then with our second boundary condition, where we know at x equals 0, m of x is equal to m naught over 2. We have our moment at that location will then be related to negative EI times the second derivative of deflection with respect to x. All right, evaluated at x equals 0. And so once again, now we got to kick back to the other page, look at the second derivative table, and we're looking for the second derivative of b beta x, right? Because this is the only term that's left. It's a little confusing because this is only 0 for this condition, right? That boundary condition. We're looking for this term because we know that C4 is equal to 0, meaning that goes away. So we want the second derivative of b beta x. So we go to our derivative table. The second derivative column is here. We find the second derivative of b beta x, and that's related to d beta x by negative 2 beta squared, that factor, okay? So you can say the second derivative of b is equal to negative 2 beta squared times d beta x. That's the useful form that we're going to use in our solution on this page here. So we've got, whoops, there we go. So we've got m naught over 2 is equal to negative EI times, in brackets, negative 2 beta squared times capital D beta x. And since we're evaluating it at 0, I'll leave it as that, and I'll just make a note in a moment. All right, times constant C3, and then again just plus 0 from C4 being equal to 0. All right, so since beta x is equal to 0 in this scenario, we already determined that d beta x is 1. So that means m naught over 2 is equal to negative EI over, nope, wrong line. It's equal to negative EI times negative C3 2 beta squared. All right, which gives us constant C3 is equal to m naught over 4 beta squared EI.
You might have to
the other page.
Yeah, I think that useful term that we use from the one you just wrote down.
Yeah, so I did write it down up here too. It's this. The negative 2 beta squared times b beta x, d beta x. That's equal to the second derivative of b beta x. Yeah. I can jump back to that in a moment, but some folks are still writing down from this page, so I'll just leave it here for a second.
So then C beta x and A beta x, are those associated with the increasing term that would be eliminated?
Not necessarily. I mean, we're just not using that term at all. But the A and C, those will show up if we evaluate, for example, slope or shear expressions.
Oh, okay.
So you'll see that here in a moment. Yeah. Yeah. All right, so yeah, I can jump back to that other page here. Yeah, because if you look at look down the derivative tables, right? So let's say we started with, or I don't know, right? So if we were taking the first derivative of the moment equation, or the deflection equation, excuse me, taking the first derivative of that moment deflection equation, that would relate us to C, right, from B. And then the third derivative of B would relate us to A. Yeah.
It's all like cyclical, right? Like
Yeah.
so like the fourth derivative of A is just itself.
Oh, yeah, yeah.
Right.
I guess it would be.
Because
Yeah.
third derivative of A equals D, and then derivative of D equals A.
Yeah, I mean, it would be modified by a factor of beta something, but yeah, you're right. It would be A related to A at the fourth level. Yeah, fourth derivative. Yep, good observation. All right, so now we've got the two constants. And so at this point, remember that we defined lowercase k, right, which represents the foundation modulus, as 4 times beta to the fourth EI. Or technically what we did is we defined the term beta in terms of k and EI, right? Beta to the fourth. So starting with a problem where you're likely to be given a value for beta or assume a value for beta, you can relate it back to the stiffness modulus with this expression. And then we can also use that term to manipulate our equations moving forward in the analysis to simplify things. So we can then say that our constant C3, for example, is equal to m naught beta squared over k. And then we can write the full expression for our deflection equation as m naught beta squared over k times capital B beta x. And if we want to, right, we can then substitute back in the full expression for capital B beta x. Which involves e to the negative beta x and sine of beta x. So if we had values to plug into this equation, we could either use this form and plug in values for beta x in radians, or we could just calculate beta x and go to the table and get an approximation if it's not an exact match or whatever. So either way, just make sure that if you do calculate it directly, you plug everything in as radians. And then for slope, right, we would just take the first derivative. So we would have m naught beta squared over k. And then as I pointed out earlier, right, the first derivative of b beta x was 1 over beta times c beta x. Or no, I got that flipped up. The first derivative of b beta x is beta times c beta x. So we'd have m naught beta cubed over k times capital C beta x. And then for moment, once we get to moment, we have to remember to include the EI term. All right, that's something that often gets forgotten and omitted, but it's an important one. Because when you have values to plug in, it'll make a huge difference. All right, so this is the relationship between the second derivative of b and d. And then from shear, that's the third derivative of deflection. All right, so we'll simplify these terms a bit. First, just like this. All right, and so now it might make more sense to factor k back out of the expression as it starts to get a little bit unwieldy. So we've got beta to the fourth EI term here, and that is equal to k over 4. So we can simplify this to m naught over 2 times d beta x. And similarly, we can simplify the shear expression as negative m naught times beta over 2 times a beta x. And so notice that all of these results, right, are in terms of the applied force, applied load, right? In this case, it's m naught. If you had a point load, all your results would be in terms of p naught, okay? Questions?
Where's the, maybe I missed this, where's the EI?
Where does the EI come into play?
Yeah,
So,
why are we just adding epsilon to it?
so that goes back to the beam deflection relationship, right? So moment is equal to negative EI times the second derivative of v with respect to x, right? Yeah, so with slope, you don't have to do EI in there because it's just, slope is just the first derivative of deflection. But moment is equal to negative EI times the second deflection of, the second, what did I say? The second derivative of deflection, right? Yeah. All right. So now we'll roll into the distributed load consideration. So here, there are two approaches that we could take if we have a distributed load on the beam on an elastic foundation. One would be to include the expression for that load in the differential equation. That's one option. Another option is to use superposition, essentially treat that distributed load as a series of point loads and sum them together, right? So that is the approach that we're going to take in this class. So I will note that. So we treat Q of X as a series of point loads. And that gives us an easy starting point because we already have on one of the previous handouts, which I'll go back to in a second, we have an expression for the deflection of a point load on the deflection due to a point load on an infinite beam on an elastic foundation. So I'll write it out. So that is equal to beta times P naught, which is the point load magnitude, over 2K times A beta X. And this is from, it's labeled figure 31.2. So I'll point it out again in a moment.
What was that figure, by beta?
Um, P naught,
You know,
yeah. So a couple pages back, this guy right here, all right, we have a point load on an infinite beam on an elastic foundation. It's this equation right here that I just wrote down. All right, so that's where that comes from. That represents the deflection equation, all right? So I guess earlier I said it was the maximum value, but since we've got X built into it, it really represents the whole thing. All right, so if we apply this to a consideration of a uniformly distributed load, rather than a load that might vary in magnitude with X, it would be the deflection at a point, right? So we'll consider our point where we're calculating the deflection, this capital Q. It would be the deflection of that point defined by a specific coordinate, all right, due to this distributed uniform load at station X. So I'll write that down and then I'll break it down. But essentially, station X represents the location of the response. So Q in this case is station X. So for a given finite segment dx of that load and along that length of that beam, what this expression would evaluate would be the contribution of the load over dx to the deflection at point Q. So I'll note x is the location of the response. So if we take the portion of the change in deflection, this equation, just due to that finite length, right? We'd have beta times Q naught dx. So we're just substituting Q naught applied over this finite length for our point load P, divided by 2K times A beta X. And that's the contribution to deflection at Q, right, which is the location of the response that you're evaluating, from Q naught dx which we're plugging in for P naught. So then that sets us up to be able to integrate that equation for the total deflection at that point, or we could evaluate this expression at every point and then sum. And this is a little bit redundant because I already kind of wrote it down, but since this is somewhat of a confusing topic, I will reiterate it. The coordinate xy, right, which represents Q, as noted above, it's the location where deflection is computed. So I'll just make one last link to that. That's Q. All right, so in the last few minutes, we'll set that up and get our starting point for this process. And then on Friday, we will apply it to an example. So we have our deflection at Q. Good luck. Got to proctor the statics exam. How many students? 200?
190.
190?
Yeah. They're all in a giant circular auditorium and around me.
Oh, okay. All right. Hope it goes well. All right, so our deflection expression at point Q, right, evaluated at point Q, is beta times lowercase q naught over 2k times the integral of a beta x dx. And so first we're just going to consider the scenario where the point where we're evaluating deflection falls within the length of the distributed load. If it falls outside, we just have to be a little bit more creative with how we define our integral boundaries. But first we'll just stick with how we've got it noted here. So in this case, right, point Q where the deflection is evaluated, we define dimensions lowercase a and b as from that point to each end of the distributed load. So we would then break up our integral according to that. So q naught times beta over 2k times the integral from 0 to lowercase a of capital A beta x dx plus the integral from 0 to b, and that's lowercase b, of capital A beta x dx. And then if we go back to that integral table, and I won't switch the pages since you're still copying stuff down, but that integral table will tell us that the integral of a beta x is equal to negative 1 over beta times d beta x. So our deflection at point Q then would be lowercase q times beta over 2k times 1 over beta, and then in the brackets I'll have the integral evaluations. So I pulled the 1 over beta out front, and then I'm going to distribute the negative sign in the integral evaluations. All right, so normally we would evaluate at a and subtract the evaluation at 0. I'm just going to flip that to account for the negative sign here. So we have d at beta 0 minus d at beta lowercase a plus d at beta 0 minus d at beta lowercase b. And from the previous example, right, we looked at d evaluated at beta 0, and that goes to 1. All right, so these two terms will go to 1. So we're left with q naught times, let's see, now the beta's factor, right? So we just have q naught over 2k times, in brackets, 2 minus d evaluated at beta a minus d evaluated at beta b. And so I'll just note here, right, lowercase a and b are measured from Q. And then just as a refresher, right, beta to the fourth is equal to k over 4ei. Questions?
Is A always the bigger of the distances?
It doesn't have to be, no. Yeah, it doesn't matter really. Pretty sure that's true. Yeah, for the point inside the load distribution, it doesn't matter. But once we get beyond the load distribution, it will make a difference how you define the order in which you define those. So we'll talk about that on Friday. But yeah, for now, that's all.